Your company is launching a new product next week, and you have to train a remote workforce of 2,000 people immediately. The production instinct is almost always the same. You sit an expert down, ask them to adopt a formal demeanor, maintain direct eye contact with the lens, and drop their face into a small box in the corner of the screen while a dense slide deck plays in the background. This specific layout, the static desk and the continuous eye contact, mirrors the 20th century broadcast television set. It is a visual language inherited from news formats, where the goal is distribution rather than skill acquisition. A format built to deliver evening headlines often conflicts with the biological reality of how human working memory processes dual-channel, transient information. Prioritizing this aesthetic polish satisfies management's desire for a professional look, but it yields a training asset that resists the adult learner trying to extract actual skills from it. To understand why most of these videos fail, we evaluate them through the empirical framework of cognitive load theory. The human brain has a strict, finite limit on the amount of novel auditory and visual information it can hold at any one moment. This stark blueprint represents the learner's working memory buffer. Designing effective training requires engineering video interfaces that align with this cognitive architecture, rather than ignoring it. We can systematically dismantle the standard corporate video tropes and replace them with evidence-based alternatives, beginning with how we film physical procedures. When every second of processing capacity counts, every pixel on the screen must justify its pedagogical existence. The first challenge is teaching a procedural, manual task. This could be assembling a physical component or navigating a new hardware interface. The standard production setup places the camera across a desk, facing the instructor as they perform the action toward the lens. This side-by-side study demonstrates how this camera angle damages the ability to replicate motor sequences. If we focus solely on the right half, we see the traditional third-person angle. To replicate these actions, the learner pays a mental transformation tax. Working memory has to exhaust its capacity continuously rotating the instructor's hand movements 180 degrees to map those actions onto the viewer's own perspective. The cognitively optimized solution is moving the camera over the instructor's shoulder to capture a first-person perspective. Shooting over the shoulder entirely eliminates the mental translation requirement. The visual input maps directly onto the learner's existing procedural motor schemas. The rules shift when we move from physical demonstrations to conceptual lectures involving charts and slides. Here we encounter the picture-in-picture fallacy, the assumption that pinning a continuous video of the instructor's face over a complex data graphic humanizes the content. Instead, it creates a split attention effect. The learner's visual processing channel is forced to rapidly ping-pong between decoding the data and reading the instructor's facial expressions. This split-screen diagram illustrates the principle of temporal continuity. It acts as the antidote to static, overwhelming slides that present all their information at once. An instructor actively drawing elements on a board while speaking naturally segments the pacing of the information. It perfectly synchronizes the auditory and visual channels. Stripping away the decorative corner box and utilizing live drawing prevents visual overload and anchors the learner to the exact point of instruction. If continuous talking heads are distracting, the logical question is whether we should remove the human instructor from the screen entirely. Human presence is highly effective, provided it is utilized as a functional tool rather than a static fixture. This schematic demonstrates the concept of gaze guidance. When the instructor physically shifts their gaze and points at the board, it acts as a signaling cue. It directs the viewer's limited attention precisely toward the target information. The secondary function of the instructor's presence is conveying positive affect. Tone of voice and body language build social connection, which research links to higher performance on delayed transfer tests. On-camera talent must be deployed to actively guide attention and build rapport, not merely to occupy empty pixels in the corner of a screen. We must address the inherent structural flaw of the video format itself. It is transient. The information disappears before the brain mentally organizes it. The continuous, unstoppable flow of a timeline naturally induces shallow, passive viewing. This guarantees rapid cognitive decay of the material you are trying to teach. The solution is artificial friction, applied through the segmenting principle. You have to force hard stops after every major conceptual chunk. This is the only way to prevent the learner's working memory buffer from overflowing. During these pauses, you inject generative activities. You force the learner to physically interact with the material, such as typing out a one-sentence summary of the segment they just watched. You can apply a similar filter to subtitles. On-screen text should only appear for novel, technical, or second language terminology. Duplicating every spoken word overloads the visual channel. Forcing a generative task during a hard pause commands the brain to actively consolidate fleeting visual data into permanent long-term memory structures. Look at the contrast between the broadcast-style corporate video and this cognitively engineered approach. We removed extraneous load. The third-person camera angle is gone, and the distracting talking head boxes have been eliminated. We guided essential processing. We utilized temporal drawing, physical pointing, and strict gaze guidance to shepherd the viewer's attention exactly where it needs to be. And we enforced generative processing. We broke the timeline into segments and demanded active recall through summarization tasks. Removing these broadcast tropes and adding structural friction creates a system that functions as an active cognitive interface. Instructional designers operate under immense pressure to deliver materials that look glossy to internal stakeholders. This checklist details the 8 criteria for effective video production derived from cognitive load research. Use this empirical data to push back against demands for outdated visual formats. Effective learning design is validated by the successful transfer of a specific skill into the mind of the learner.